Joint work with Erika, Gomes-Goncalves and Henryk Gzyl that I'm going to present. And this is a rather long title, but I guess there are a few keywords you're already aware, like Bregman divergence and Riemannian metric, and we will see some kind of ties and different structures that they share. So to recall what is a Bregman divergence, here you take a convex function, a potential function f, and you plot this graph of this function, and then you want to measure the distance or dissimilarity between two positions like theta 1 and theta 2, and what you will do is that you will measure this vertical gap here that can be expressed as the ordinate difference between the function evaluated at theta 1 minus the function of the tangent line defined at theta 2 of the function f evaluated at theta 1. So this is strictly positive or zero if the points coincide here in your parameter space. And the formula that you will get here is just the difference between f and the tangent line evaluated at theta 1. So this Bregman divergence has been proposed in operation research a long time ago in the 60s. And it has been very popular recently in information theory and machine learning for several reasons. And what we can do also is to have a different interpretation of this Bregman divergence. Like for example here, we interpret it as a tangent line to the potential function f at theta 2, and then I take a parallel translate that goes through the point at theta 1, and the vertical gap here everywhere is a Bregman divergence. So this is a different visualization of what is a Bregman divergence. So whenever you have a smooth dissimilarity functions that can be called divergence in information geometry, you can propose some information geometric structure, a statistical manifold here, that will be with a Riemannian metric tensor and some dual connections that are coupled to the metric, and they are defined as follows here. So you have the Riemannian metric that will be defined by a second order derivative and the connection by three order derivatives. Okay, and in the case of when D is a Bregman divergence, these things come much simpler, because what you will have is you will have a Hessian structure where your Riemannian metric will be the Hessian of the primal potential function, and then you will define the dual potential function that is also convex here by taking the legendre transformation of your primal potential function, and you will have a dual Riemannian metric that will be the Hessian of the dual potential function, and you can check by the Christoffel symbols of the connections that they are dually flat. So this is why we call it also a dually flat space in that case. So Bregman divergence is also canonical divergence of dually flat structures. And we have several structural properties, like for example here you have this identity relationship, that is if you make the matrix product of the Hessians of the dual potential function, you find the identity, and you can interpret that geometrically as saying that the natural primal basis is and the dual basis are mutually orthogonal here. So another aspect of Bregman divergence is that it's also in bijection with some kind of statistical distribution that we call exponential families. And we have yesterday some nice talk about Professor Letac on exponential families. So here, to make it very simple, we start with some positive measure mu, and we consider the density functions that can be written in that canonical expression here. And the function f here is what is called the log normalizer, or the cumulant function, or partition function in statistical physics, and it is defined as a log Laplace transform here. And you have the natural parameter space that is where you have this Laplace transform that is finite. Okay, and the thing is that what we see is that if you have a Bregman divergence, I can build some statistical manifold, that is a dually flat structure, and I have dual Riemannian metrics, but I can consider also the Riemannian geodesic distance that is induced by this convex potential function here. And this is what has been called in information geometry the Fisher-Rao distance, or the geodesic distance. But one of the problems that we face in practice is that in order to compute the Riemannian distance, we need to do two things. One thing is to solve from the Euler-Lagrange ordinary differential equation the geodesic equation, And then we need to integrate the length elements along that geodesic to get the Fisher-Rao distance. So we need to do the two things to get a closed form solution for the distance, and it's very difficult in general. Like, for example, for multivariate normal distributions, we do not know any closed form solution for the Fisher-Rao distance, but we have very easy formulae for the Kullback-Leibler divergence between two multivariate Gaussians. So there's a big gap in complexity of the formulae, whether you take the Riemannian geodesic distance or the Bregman divergence that is induced by the potential function here. So the title mentioned separable divergence and separable Bregman divergence. So here again, I have the generic, I changed a bit the notation here, but this is again the Bregman divergence formulae. And we will say that it is a separable Bregman divergence if my generator can be written as a sum of univariate generators here. And here all the generators are the same, so it's a real value scalar function. And in that case, my Bregman divergence can also be written as a sum of univariate Bregman divergences for the 1D generators here. So very simple definition. And what is a separable Bregman generator from non-separable Bregman generator? Here you have a table of common domain and generators and the Bregman divergence. So you will see that most of the usual stuff is separable, but some of the divergence like square Mahalanobis distance or Keil divergence and the simplex are not separable. Okay. So the good thing is once we have a separable Riemann divergence is that the Riemannian metric can be written very simply as a diagonal metric. So here we will have the metric tensor that will be just the second derivative of our scalar generator, and this is a Kronecker symbol. And we can solve the ODE of the geodesic very in a simple way. So we will find that the geodesic distance is the square root of that, or the square of the geodesic distance is this expression here. And for writing this expression, I will introduce a mapping transformation H that is defined as the anterior derivative of the square root of the second derivative of phi. Okay, so it's an increasing continuous differentiable function. Okay. So the geodesic, once you have this diagonal metric, will be simply written as follows. For each coordinate of the geodesic, you will find that you have some kind of quasi-arithmetic mean, or Kolmogorov-Nagumo definity means. And again, I will call you what is the mapping here, H. Okay. So the geodesic equations are in closed form and easy solution. So because once we have a Bregman divergence for a potential function, we have also the dual Bregman divergence, we may ask ourselves what is the dual Riemannian distance from the dual potential function. So again, here, what we plug the legendre convex conjugate function, and here we make this kind of dual parametrization by taking the derivative. And we find that the dual Riemannian metric here is just the second derivative of the dual potential function. And again, the Gzyl identity that I mentioned before is that thing. And I will call you that for Bregman divergence and dual potential function phi and phi star, we have this identity. And what happens for the Riemannian distances induced by the Bregman potential function is that we have this identity here. Okay. So here there's no swap. You can see that, of course, because it's a metric, it's a symmetric distance, and there's no swap in the arguments. But in the Riemannian stuff, we have in the Bregman stuff, we have the swap of the parameters. Okay, so what you can do is interpret all the stuff with this following diagram. You can see that if we have a separable Bregman generator, then the induced Riemannian geometry can be isometrically embedded by a nonlinear mapping into Euclidean space, and we have this kind of relationships here. So the function h here is this monotone embedding, and we have this identity that I mentioned before. Okay, so you can just look at this diagram and go back and forth to the even the Euclidean space after some kind of embedding, or into the dual parametrization by the Legendre transformer. So if I want to illustrate those properties with a simple example, let's take the negentropy, the Shannon negentropy, or the Shannon information. So the univariate generator is x log x minus x. So you find the derivative and second derivative like that. So because I mentioned you that to solve the ODE, you will introduce this function h, the mapping here. You will find that this is this thing plus a constant because it's antiderivative. You take the legendre differential conjugate, you find these things, and then you find the dual kind of embedding function here, which is that stuff. And you can check that you have the two Riemannian metric distance induced by this potential function as follows, and we check that we have this identity. Okay, so this is just one example that illustrates what has been explained before. And we have, of course, we can make the exercise for different kind of generators, and you will find this kind of Bregman-Riemannian distance here. Okay. So once we have such a kind of structure, we may ask, shall we cluster using Bregman divergence, or shall we cluster with Bregman-Riemann distance? And if we look at just the center-based clustering like k-means, we need to compute the centroid, and the centroid can be defined like this kind of Karcher minimization as a minimizer of the sum of the square distance here. So here we put the Bregman-Riemann distance, and what we find is that we find this thing, and this thing, if you're familiar with Bregman clustering, it looks like a left-sided Bregman clustering, but here we are with a metric distance, so it's a symmetric. Okay. And we can also analyze what are the proximity structure induced by those various distances by looking at Voronoi diagrams. So especially if we define the balls for our generator here as follows. So you can find by the isometric embedding to Euclidean isometric embedding, this is this kind of a ball. And the Voronoi cells, you can again rewrite it as follows, and with the Euclidean cells here. And here you have some examples depending on the generator that you choose of this Bregman-Riemann Voronoi diagrams here. Okay, so basically, if I give you one potential function that is a convex function, for example, here, what I can do is I can plot the 4 partition of space induced by dual Bregman divergences and induced also by the Bregman-Riemann distances. So you have this kind of color code here to show how the proximity and the Voronoi cells change according to the chosen distance. Okay. In the report here, there's some in extenso analysis of clustering properties of the distance compared to Bregman divergence, and we did it for k-means, expectation maximization, and hierarchical clustering. So there's some kind of quantitative analysis of the performance of each of those algorithms. So I refer you to the report for more details. Just to conclude, I want to mention that the Bregman divergence originated in the operations research community, where the goal was to find, given a set of convex objects, a common intersection point, if it exists. And it was, the method that was used at that time was called alternating projection, where you start from some initial point, and then you project of the first constraint. Then this point you project on the second constraint, and then you cyclically make projection on the constraint. So after the second constraint, if I have 2 objects, I go back to the first object like that. And in the limit, of course, it is only in the limit that you reach a point that is in the common intersection. And people ask themselves what kind of, so we know for Euclidean distances that it worked, and people were asking whether there are some other kind of dissimilarity measures or deep projections according to some distance by minimization. If that worked, and Bregman divergence were introduced in that context in the 60s. Okay, and this kind of alternating minimization procedure for finding distances is also very useful to find a distance between 2 submanifolds or 2 statistical submanifolds, and of course people ask condition for which you have convergence and where this distance is unique by this alternating projection minimization. And you have a well-known result in information geometry that says that if one convex is is a primarily flat and the dual is a dually flat, then you have convergence and unicity. Okay, to conclude, let me summarize what I've been mentioning in this talk. We introduce some new explicit formulae for the Riemannian geodesic distance where we have separable Bregman divergence, and we studied some properties, including the Voronoi diagrams of that that structure. And then we apply different clustering algorithms like k-means. And also in the paper we have more details about fixed weight quantization and best predictor using this geodesic distance. Okay, thank you.